Okay, I'm going to get started. Just for the avoidance of doubt, I'm not Brandon Rhodes, who was on the monitor outside. He's next. I'm Mike Lee Williams. I'm a research engineer at Cloudera on the Fast Forward Labs team, which is sort of the machine learning services and applied research team. Today I'm going to be talking about serverless for data science. Just a housekeeping note. I was going to do a bunch of live coding, but the Wi-Fi isn't quite up to it. So all the code I would have executed, and I will show you, is on GitHub, along with links to the slides and links to a bunch of the resources I'm going to mention. Also, I've got quite a lot to squeeze in, so I'm afraid I may not have time for Q&A. As an audience member, I generally find that no great loss, but please do come and find me afterwards if I don't have time and you have questions or you just want to chat, or my contact information is up there. Okay, let's get started. These are computers, and I think, if you're at this conference, we generally agree that these things were a mistake. Hardware in particular is very bad news. And one of the wonderful things about the cloud is that the actual hardware is someone else's problem. Amazon and Google and Microsoft do such a wonderful job of taking the feeding and care of the hardware that you can basically forget it exists. You can put it in your mental trash can and forget about it, which is wonderful. There are a couple of downsides to moving to the cloud. This is one of them. It can be a relatively efficient way of setting fire to piles of money, which is, suboptimal for various reasons. There are many complicated reasons why the cloud can be expensive, it can be cheap. We'll get into some of them, but one of the high-level reasons is you can end up with long-running, quite high-powered hardware or services sitting in the cloud somewhere, and inevitably they may not be 100.0% utilized at all times. So you have an overhead in your infrastructure that is underutilized, and that implies increased costs. And of course, migrating to the cloud doesn't solve this problem. When you move your hardware into the cloud, you still have an operating system or container technology, and that implies you've got a thing you've got to install, configure, maintain, and secure. And this is recent footage of me installing, configuring, and maintaining an operating system. It's not an easy thing to do. It's a never-ending task. It's personally not something I particularly enjoy. And from the point of view of most of our employers, it's not how they make their money. They make their money by solving business problems for users. At the application level is where they make their money. So ideally what we'd like to do is this, not just forget about putting the mental trash can, the hardware, but also the next level up, the operating system, the container technology, all that nonsense, and just focus on the application. That is the claim or the goal or the conceit of serverless. So let me say a little bit about what serverless is. I've got a business idea. I've got a unicorn idea, or I think it's going to be a unicorn. I'm going to offer an API to my users that adds numbers together, and I think this is a winner. So along comes a request for what's 2 plus 2. In a serverless deployment, some kind of long-lived gateway intercepts that request and summons out of thin air some hardware. The hardware then performs the computation. The result is 4, obviously. And then crucially, the hardware dies a noble death. It goes out of existence having solved that one problem. Along comes my second user, business is going really well, and this person wants to know 37 plus 5. The same thing happens. A server is summoned out of thin air, performs the calculation, and then goes out of existence. Serverless is serverless in the sense that in between these two requests, I had no servers. I had no infrastructure. And in a more realistic situation, I might have always some infrastructure, always some requests coming in. But the amount of infrastructure I have scales linearly with the amount of requests I'm getting. And crucially, for the data scientists in here, that linear relationship has an intercept pretty close to 0. That means my costs potentially go down to a very small number, if not 0, in this kind of deployment. I think serverless is kind of a misnomer, to be honest, though, because you tend to have a lot of servers. Those of you who know what Bayesian non-parametrics are, Bayesian non-parametrics isn't non-parametric. It has tons of parameters. It's a really bad name. Serverless is the same deal. But the point of serverless, of course, is to get rid of the problems associated with orchestrating a very complicated system like that. So generally, we're going to pay someone else to do it. And these are the options. We can pay AWS, Google, and Azure to do this. The best known is probably, and I think the most mature, is AWS Lambda, and that's the back end we're going to be using throughout this talk. If you have very particular needs or your own private infrastructure, then there are roll your own serverless solutions that you can deploy, have a serverless as a resource in your organization, and OpenFast is perhaps the best known of those. Let's actually do something on AWS Lambda now. So imagine we've got this web application. Don't worry if you're a data scientist, data science is coming. But for now, we've got a very simple web application. There's some boilerplate at the top and the bottom here that if you haven't seen Flask before may look a bit intimidating. Don't worry about it. Just look at the function time. What that's going to do, hopefully, obviously, is return a string that is the current time. Immediately before that function, there's what's called a decorator, which Flask uses to wire together URLs to Python functions. And what that means is when someone visits our website /time, the result of that function is returned to the user. So here's our web application. I can deploy that locally like this. If I just run it, I get a very helpful message telling me it's running on 127.0.0.1, port 5000. And if I then visit that URL /time, I get the time back. And I was writing this talk at 9 at night a couple of days ago, so that's why the time is that. Which brings us to our first use case for serverless. Obviously, if I want to share this application with the world, my laptop is not a great place for it to live. I have aspirations to close the lid on my laptop occasionally. I'd rather not deal with the firewall complications of that. So I'm going to deploy it on AWS Lambda. And here's what doing that looks like. There's a lot of plumbing associated and bookkeeping associated with deploying on AWS Lambda. You can do it yourself by clicking a bunch of things in the console or figuring out the AWS API. I don't recommend it. I recommend using a tool instead. And there are 3 options that I know about. Zappa is the one we're going to be using throughout this talk. Chalice is AWS's official version, which I haven't used. And then there's one that's confusingly called Serverless, or sometimes the Serverless framework. I've never used that one because the installation instructions referred to the node package manager. And I was like, not today, Satan. But here's how you use Zappa. So the first thing you need to do is put yourself in the directory of your application and create a fresh virtual environment. If you're an Anaconda person, I'm sorry, you're going to have to learn about virtual environments to put stuff in production. So we create a virtual environment, and in that virtual environment, we install the dependencies of our application. This is all happening locally on my laptop. And in this case, the only dependency is Flask. Then I run Zappa in it, and you know Zappa's a cool tool because we've got some ASCII art. And you get a Q&A, like 5 or 6 questions. Zappa is able to infer some things from your application, make sensible assumptions. And at the end of that Q&A, it writes a settings file. And this is the settings file you'll get for this application. The application is on GitHub. And I got this settings file by pressing return 6 times. So this is really advanced DevOps stuff. And the only interesting thing about this is the very first line. Zappa has inferred the Python location of the thing I want to use to respond to web requests. Namely, it's in the module app, the file app.py. There is an object app that is going to handle these requests. Then, to deploy, it may not surprise you to learn that the command to do that is Zappa deploy. And there's a tremendous amount of nonsense happening here, of bookkeeping that we could do ourselves, but Zappa takes away the need. The interesting thing, or the important thing from our point of view, is the last line, which is the public URL that anyone can access that will respond with this web application. The only interesting thing I want to flag up in the output of this command is the bit where it says packaging project as zip. What's happening there is it's creating a zip file containing not just my application, but its dependencies. And Zappa's definition of its dependencies is the things it finds in your active virtual environment. And that's why I said create a fresh virtual environment. Don't use one with Keras and PyTorch and Notebook installed, because you're going to end up copying that up to AWS Lambda, and that's a bad scene. But it's deployed, and now I can curl that URL and get the time. And it turns out that AWS runs its servers on UT, which I suppose is the least bad option they have. So instead of 9:30 at night, it's 4:30 in the morning. In the notes for the talk, if you go to the GitHub URL, there's a couple more steps here where I make this server know about time zones and offer URL parameters. And in particular, relevant to using Zappa, I show you how to debug an error. Zappa provides a tail command that consolidates all the errors from the various moving parts that Zappa orchestrates and allows you to, for example, inspect the Python exceptions that make debugging relatively easy. That gets past one of the criticisms of serverless generally, which is that it's got a lot of moving parts and it can be quite difficult to debug these remote functions. So let's look at another thing you can do with serverless, and that's cron jobs. Cron jobs, for those of you who don't know, are jobs that recur on a regular schedule. On Unix, they're called cron jobs, and AWS Lambda has an idea very similar to that. I have a deployed cron job, which is a couple of Twitter bots that tell me the weather early in the morning in Los Angeles and New York City. And I don't actually know what a Fahrenheit is. So I made these Twitter bots tell me whether it was warmer than yesterday or colder than yesterday, which makes things simpler for me. Turns out 109 is pretty hot, by the way. That was earlier this year. This bot is an AWS Lambda job, and again, I deployed it using Zappa. The configuration file ends up looking a bit more complicated, but I want to just flag up the bits in bold here. You can see literally a cron tab line there. That's one way of specifying a recurring job on Lambda. And then you've got environment variables. That allows me to inject configurations such as API keys into these instances. So that was all how to do web operations, cron jobs, system stuff on the cheap. And this is a data science talk. So I do want to move on. I want to flag up the advantages of serverless now before we get into the data science. There are a couple of big ones from the point of view of the operations and, let's say, traditional software engineering community. We're focusing on the business logic here, and we're getting scalability for free. That web application scales up essentially infinitely. But the advantage that interests me most is this one. If you migrate to serverless, you get 6 filthy dollar bills and some Scrabble tiles. It's cheaper. And that's because we're paying for it in almost exact proportion to our usage. When we're not using it, we're not paying for it. And that has implications for data science that are at least as interesting as the implications for traditional web operations. But I just want to give a war story, not mine, from the web operations community. This is my great Medium article, very worthwhile reading, about moving a fairly substantial web API that was running on EC2 that cost $10,000 a month to AWS Lambda. And when they completed that move, the cost went from $10,000 to $370 a month, which is obviously a huge, huge win. Now, it's not all sweetness and light. There are a couple of problems. Serverless shares some characteristics with microservices, and one of the criticisms of microservices is you've got a lot of moving parts, complexity, debugging can be tricky. And it also shares some criticisms with the cloud generally, and perhaps the most salient of those is vendor lock-in. Those 3 options I showed you, Azure, Google Cloud, and AWS Lambda, are not API compatible. You can't just copy serverless applications between those 3 things easily. Those disadvantages are real, and it's important to acknowledge them. But for our purposes, there is a disadvantage that is much more salient. And it's not so much a disadvantage as the inherent premise of serverless. And it's that these machines pop in and out of existence. And they have restrictions. They are underpowered machines, not quite this underpowered, but they actually come with usually a maximum of 1.5 gigabytes of RAM on AWS Lambda. Very small amount of local storage as well. And secondly, they're living on borrowed time. On AWS Lambda, your Lambda function has to return within 300 seconds. Otherwise, you're out of luck. You don't get the result. So the numbers I said there are kind of arbitrary. 1.5 gig, 300 seconds. Amazon could and probably will change those numbers. And if you feel very strongly, you could deploy OpenFast and choose whatever numbers you want. But the fundamental premise that these are short-lived machines doesn't go away. And it has the implication that they have no state. They have no memory of what happened the previous time that function was invoked. And when several of them are existing at the same time, they have no direct way of communicating with each other. We could use a database. We could post to Twitter and call that a side effect. But if all we use is AWS Lambda, we have to only use pure functions, by which I mean functions that take input, give output, and have no side effects. And that potentially is quite restrictive. So data science, finally. Here's a picture of data science. We've got these machines with no internal state, and they're not very fast. And that doesn't seem very promising. But crucially, potentially, we've got a very, very large number of them. And we only pay for them while we're using them. And that raises a very, very interesting possibility for data science, which I first heard about in this paper. This is a paper that came out in February of last year, Occupy the Cloud, Distributed Computing for the 99%. If you've never read a CS paper, or if you haven't read one for a while, I really recommend this paper. By the standards of CS papers, it's quite informal and readable and a lot of fun. So highly recommended. But it's interesting to us in particular because it's the place where a tool called PyWren is introduced, which is the tool I'm going to be talking about for most of the rest of this talk. PyWren is a tool that maps functions across parameters using AWS Lambda as the computational backend. So first, what do I mean by maps functions across parameters? This is what I mean when you're doing that locally. Here I've got a function square that returns the square of a number. I want to apply that function to these 6 numbers, 0 to 5 inclusive. If I'm being Pythonic, I'll do that with a list comprehension. If I'm being a Haskell nerd, I'll do that with a map function. But it's the same basic idea. The arguments of the map function are the function you want to apply and the things you want to apply it to. Map in Python 3 is a little bit indirect. You don't directly get the answer back. You get this weird map object that is sort of pregnant with the possibility of the results. So when you call list on it, you get the results. I mentioned Python 3 here, complete sidebar to this talk. If you're a data scientist, you should be aware that a little library called NumPy, the new versions will no longer support Python 2 starting in January 2019, which I know seems like the future, but is 4 months away. So we should all be on Python 3 in this room. But let's map this computation, not on our local machine, but let's spin up 6 AWS Lambda instances to perform this not terribly demanding computation. Here's how you do that. Import PyWren. Create one of these executor objects. The executor object has a method map, which has exactly the same calling signature as the built-in map function. It takes the function and the thing you want to apply it to. Again, just like Python 3's built-in map function, it doesn't directly give you the answer. It gives you this weird list of futures objects. If you know what a future is, this is those. If you don't know what a future is, you don't need to. It's a thing with a result method that gives you the result. So we can do something like the last line here, this list comprehension, and accumulate the results. So here's how we get the answer. What's actually going on behind the scenes? One of the unfortunate things about me not live coding is you can't see how long this took. So let me put my cards on the table. The x-axis here is time, and the scale is in seconds here, and we've got rows of dots corresponding to the 6 workers. So the entire job takes of order 10 or 20 seconds to multiply 6 numbers by themselves. So this is not a net win compared to my ancient 2013 laptop. We'll talk about why it's worth it in a second, but I want to spell out what PyWren is doing here. First comes host submit, and what that means is it's packaging up the application and copying it up to S3 and then launching these 6 AWS Lambda workers. They start, that's task start, and then they download their marching orders from from S3. And additionally, they download an Anaconda Python installation. Unlike Zappa, which packages up your virtual environment, PyWren has an opinionated set of dependencies that come with that are available to every PyWren worker, which is a good thing overall because many of the typical data science libraries can be a bit tricky to get working on AWS Lambda for various reasons. So that's a nice thing overall. It does result in some weirdness sometimes if your version of a library is a bit different to the one in their opinionated Anaconda runtime. But then it launches, computes the result, each worker writes the result to S3, and then our client, the laptop, copies those results down. And the whole thing, that was a mouthful for me to describe what's going on, and you can perhaps understand why there's significant overhead here. So we probably wouldn't use this kind of thing for something that took essentially instantaneous amount of time. But for jobs that take several tens of seconds, when we want to do lots of them, this is a huge win. And I think the other thing to note is that it is API compatible with Python's built-in map function. So you can migrate your code to PyWren immediately by doing this. And I see cameras coming out taking a photo of this. Don't do this. This is just to make a point that it's a drop-in replacement for the map function. If you redefine it, things will still work, and you'll just be using Lambda as your backend. You should think about which parts of your application parallelize well, and we'll talk about what I mean by parallelize well right now. So we saw use case number 1, web operations on the cheap, cron jobs. We're now ready to talk about what PyWren is actually doing, which is embarrassingly parallel calculations. So what does embarrassingly parallel mean? Here is a field of carrots, and we want to harvest the carrots. We have a tractor. We've got, what is this, 8 rows of 10 carrots here. Let's say the tractor can pick up the carrots 1 per second. So clearly this tractor is going to take 80 seconds to harvest the field. If we're willing to deal with the overhead of owning a second tractor, we can harvest the field twice as fast. These 2 tractors are going to do it in 40 seconds. And if we've got the cash for 8 tractors, we can get this field harvested in 10 seconds, which is wonderful. This job is embarrassingly parallel. And the reason it's embarrassingly parallel is these 2 tractors do not need to talk to each other to get the job done. They can work completely independently. They just have to agree before they start, these are your rows of carrots and these are my rows of carrots. But while they're harvesting, they don't need to pass carrots between them. That's embarrassingly parallel. And our square function was also embarrassingly parallel. In order to calculate the square of the number 3, you do not need to know the square of the number 2. So when you're looking at your application, thinking, what am I doing that's embarrassingly parallel? Anything you're doing in a list comprehension is almost certainly embarrassingly parallel. Certainly anything you're doing with a map function, the same thing applies. If you're using a for loop, it might be embarrassingly parallel. It's possible and quite common to write for loops that are not embarrassingly parallel, that have side effects. So you have to think a little bit more carefully about for loops and whether they're a good candidate. But let me now show you, instead of a toy example where the overhead of AWS Lambda is not worth it, a real example from my own work that saw a huge speed up with AWS Lambda and PyWren. Unfortunately, if you're a data scientist, you probably want to spend most of your time noodling about with PyTorch. But in practice, what many of us spend a lot of time doing is web scraping. And I wanted to scrape the abstracts of a conference called NIPS, a machine learning conference. The code and the data is online if you're interested. And I wanted to do this on AWS Lambda for a couple of reasons. Firstly, I was scraping them locally 1 at a time. If I'd have been really clever and used the multiprocessing module or something like that, I could have done them 4 at a time on this laptop. Or I could have written some asynchronous code and turned my brains inside out, which is no fun, and done it even faster. What I wanted to do is just change 1 line in my code and do it on AWS Lambda. The other reason I wanted to use AWS Lambda is it turns out that AWS, the organization, has a slightly faster connection to the internet than Time Warner is able to provide me and my laptop at home. So by migrating to AWS Lambda, I saw a huge speed up in this. One thing to note that's going on here is I'm mapping a function not across individual papers, but across batches of papers. And that deals with the fact that spinning up these Lambda instances has an overhead. It's not worth scraping 1 URL because it takes 20 seconds for the thing to start up. So instead, I send it a batch of, I don't know what it was, 100 papers or something like that. And then the overhead is not just worth it, it results in a huge, huge speed up. So that's web scraping. Perhaps more glamorous from the data science point of view is doing a heavyweight numerical calculation. Black-Scholes is a partial differential equation that in practice completely fails to predict the evolution of the price of options, but people like to solve it for whatever reasons. Bradford Lynch wanted to solve it 305 million times. It's a fairly heavy numerical calculation, but again, with really 1 or 2 changes to his code, he was able to shift that onto Lambda as a backend using PyWren. And if you can see down there in the 3rd last line, he saw a 270x speed up when he did this, a huge speed up. And again, when all was said and done, he wasn't paying for the cluster after he'd finished his work. It was on borrowed time, and he stopped paying for it as soon as it was finished. On the GitHub link I mentioned at the start, there are also examples of long-lived, embarrassingly parallel jobs that are kind of part of an ETL data engineering pipeline, things like video encoding. But I personally find this interactive PyWren use of AWS Lambda more interesting. That's because I think it's this use case where the cost savings of serverless are most apparent. And that's because if you think about how you do data science, if you think about how you complete an analysis, you spend most of your time staring at exceptions and trying to figure out what's going on, or going off to get coffee and giving up. It's one of the wonderful things about Lambda is you're not paying for the cluster while you're getting coffee, while you're banging your head against a brick wall, while you're leading a rich personal life and not doing data science. The infrastructure goes away when you close your eyes or when you're done. And that is really, I think, a very, very compelling possibility. So I want to tie things up with both PyWren and with PyWren and Zappa. I'm going to train a machine learning model using PyWren to parallelize the hyperparameter optimization. Then I'm going to deploy it using Zappa. So here I've got some training data. I've got two blobs, purple and yellow, and clearly I want to fit a classifier that can distinguish between these two models. If I were to do that locally, if you haven't seen scikit-learn before, this is roughly what it looks like. I'm going to train a k-nearest neighbors classifier, and if I do that, I get the last thing on the screen here, 83.8% accuracy. Pretty good. The important thing to note here is the second line there. When I instantiate the classifier, I give it what's called a hyperparameter. A hyperparameter is essentially a magic number that determines some characteristics of the model independent of the training data. But it's not completely independent of the training data because you do choose it on a problem-by-problem basis based on characteristics of the training data. What's going on here with k-nearest neighbors, the particular hyperparameter is the number of nearest neighbors. K-nearest neighbors is very simple. To classify a new point, you find the k nearest points in the training data and have them take a vote on the class of this point. And the question is, what's k? How many points should get to vote? And I've chosen 5 here and got a pretty decent accuracy. But the question is, I'm worried, could I have chosen a better number? Obviously, this is a toy problem, but at a larger scale, I would like to parallelize that question. And it turns out it is embarrassingly parallel. It is the dictionary definition of embarrassingly parallel, trying all those hyperparameters. Essentially, what I'm looking for is which choice of parameter gives me the best accuracy. So here we go. Remember, PyWren's map function needs the function it's going to map and the things it's going to map across. So first we'll set up a list of hyperparameters. I'm going to try the numbers 1 to 8 for k. And then I've got a little function, train model, that is going to take one of those hyperparameters and train a model with that choice and return the classifier. So given that setup, I can now use PyWren to map the computation. So it's stuff you've seen before. We're using PyWren map, and then we're going to collect all the results. And the crucial thing to note here is that previously we've seen PyWren used to accumulate fairly simple objects, fairly simple data, numbers, strings of text, things like that. What we're getting back from S3 here when we call this PyWren job is a rich Python object that has survived being pickled and unpickled. This is the scikit-learn classifier with attributes and methods. And we get it back and it works locally on our machine. And we can evaluate the accuracy of these different models on our training set. And we find, indeed, there was a better choice than 5 for this data set. We could have chosen 7. So to close the loop, I'm now going to deploy this model. I'm going to throw off the shackles of my friends who act as gatekeepers to production for me, and I'm going to deploy it myself. And I'm going to do it on AWS Lambda, which means I'm going to do it in such a way that it can scale up very large. Here's my Flask application that does that. What I've done behind the scenes before this talk is copy the pickled model onto a public URL, in this case an S3 URL. My Flask application, when it pops into existence, the first thing it does is download that FITS file. FITS file, I'm not an astronomer anymore. That pickle file. And then there's a predict endpoint that takes 2 URL parameters, the 2 features of the data, the x-axis and the y-axis with those pink and yellow, those yellow and purple blobs. And then it runs the classifier and returns the string purple blob or yellow blob. And we could deploy this locally, but I just ran Zappa deploy with this. Again, this is one way you can just hit return for that Q&A about how you want to configure it. Very simple, and up it goes. So let's actually see it in action. So if the conference Wi-Fi is working, this is the public URL of it. And you can see in the URL bar I've got, let me actually just show you the train data, just to refresh your memory. We had purple blobs on the left and yellow blobs on the right. So if I put feature 1, the x-axis is a large number, 9, and feature 2 is 6, then I get yellow blob. And then if I can type like this and say that's 3, purple blob. Wow, machine learning in production. And notice the latency there. You might be thinking, reasonably, that, hang on, if you're downloading a model every time this function gets called, that seems kind of expensive to me. And it is expensive. It turns out AWS are doing some clever stuff with caching that means in practice, the second, third, fourth time you hit this API, it's much faster. So in practice, this is actually a pretty good pattern for deploying machine learning. So that was kind of a grab bag of things you can do with serverless. And I want to give you some takeaway themes. So serverless is good for web operations on the cheap. We saw that. It's good for cron jobs, these kind of periodic recurring tasks. And we saw at length with PyWren that it's great for embarrassingly parallel computation. These three things have in common that they are bursty. And that burstiness is the reason they're cheap and a good fit for Lambda. Yes, they're bursty in the sense that sometimes they require huge amounts of resources. Maybe your website becomes very popular. Your cron job is some huge computation that turns on once a week, so clearly that's very bursty. Or you decide to come back from your cup of coffee and run a new job in your notebook using PyWren. Those are all bursty workflows that suddenly become very large, but also they can go to very, very low usage, and Lambda supports that, serverless supports that in a cost-effective way. So the great thing about serverless is not so much that it's great when you're using it, it's great when you're not using it, which is kind of a weird way of thinking about it, but I think that's the right way to think about it, at least from the point of view of a data scientist. I want to be candid here. There are things it's not good for. I'm not a web operations person, and I know it has a number of limitations for deploying a complex web application. People do deploy Django applications on it, but I don't know much about that. So I'm focusing solely on the PyWren stuff here. It's not good for map, shuffle, reduce. You might be thinking some of the things I was doing there felt quite map reducey, if you're familiar with that term. Many map reduce applications actually conceal a shuffle step where the workers communicate with each other. If your map reduce operation does conceal a shuffle step, out of the box, PyWren is not a good fit because these workers can't directly communicate with each other. The PyWren team have been very creative with doing some benchmarks where intermediate results get written to S3, and you can do that if that's your idea of fun, and you will see a big speed up. But it's no longer the drop-in one-liner replacement for local computation that I sort of advertised in the rest of the talk. By the same token, PyWren is not a good fit for big, beefy linear algebra operations like matrix inversion, Cholesky factorization, these sorts of things, again, because they involve accumulating intermediate results. In order to make these things a good fit for PyWren, you have to break open the algorithm and think carefully about how to conceal that complexity to the user. And tools like Dask do a great job of that, assuming you have access to powerful computing resources on your local network, generally long-lived resources, like a Spark cluster sort of thing. The PyWren team, again, have demonstrated workarounds. Just keep an eye on what they're up to. Literally in the next few weeks, I think they're going to be releasing a NumPy-type tool that uses Lambda as the backend for some of these linear algebra operations. We saw with the web scraping example that I needed to accumulate tasks to be several tens of seconds in order for the overhead to be worth it. But I can't accumulate too many tasks. If I accumulate enough work that's over 300 seconds, no good. I have to be in a sweet spot of jobs that take longer than a few tens of seconds but less than 300 seconds for PyWren to be a good fit. And that, to be candid, not a lot of jobs are in that sweet spot. And finally, AWS Lambda instances and the instances on the other cloud providers do not have GPUs. So quite aside from the deep algorithmic subtleties of distributing backpropagation, for example, or gradient descent more generally, just as a systems problem, serverless instances are not a good fit for training deep neural networks because they don't have GPUs. So again, here's the link to the code. Here's the way to get in touch with me if we don't have time for time. I guess we might have 5 minutes. I just want to sum up by saying, remember the title of that paper I mentioned, Distributed Computing for the 99%. What I understand by that title is that there is a 1% of us, and I don't know if it's actually 1%, who are operating in companies that are operating at a scale where aggregated across the entire company, they rarely don't require most of their computing resources. Global consumption varies, but it doesn't go down to zero. Or if it does, their peak usage is such, they're operating at such a scale that it is more cost effective to just buy the cluster. and they have the fixed cost resource of data engineering, systems, ops teams to manage this long-lived resource. Serverless, in the sense that I've described it, and I think in the sense the PyWren folks have in mind, is perhaps not for those people. But the high-level takeaway from this talk, I think, is that if you're operating independently, or if you're working on a personal project, and you don't have the money, the engineering support, or the patience for heavyweight nightmares like Spark and Hadoop, then take a look at Zappa and PyWren and the serverless ecosystem more broadly. And even if you do have those resources, do check it out. I think it's a lot of fun. Thank you very much.